One of the most fundamental questions that we look at as humans is there life out there? Are we alone in the universe? And of course, it's very difficult to answer this unless, some alien actually comes up and says hi. So until we've actually sort of detected aliens, or until we've actually, seen them or heard from them or something like that, then we have to use a bit more roundabout ways to try to answer this question. So we can't directly answer it. But what we can do is start thinking more about the science behind, well, how might there be life out there? And one of the things that biologists look at is the fact that most life, well, actually all of life on Earth, is somehow related to liquid water. So we think that we need liquid water in order to have life. Now, it's very difficult to actually make that sort of statement because, of course, we only have one data point, right? I mean, if you think about it, we have one place in the universe where we know where there's life. That's on Earth. And that's the place with liquid water. Now, there are some actual deeper reasons why we think that life needs water. It turns out cells in our body and the cells that make us up, they're actually water-based. So they're H2O-based, I should say. And so because of that, and because we look at other forms of life on Earth, they all seem to be similar to that. So we figure, well, I mean, what else are we going to do except for start looking for other places that are similar to us? Now, does that mean that life could be based on something other than water? Maybe. But we're certainly not knowing anything about it, so we may as well start taking guesses with things we do know. Okay, so you might think, oh, there's no point, but there is a point. We can look at things that are similar to us and see if maybe that's possible. Now, we don't know what the life might look like, but we can certainly try to look at if there is liquid water. So the main thing here is going to be looking for liquid water. Because at least on Earth, we find where there's liquid water, there's life. So we're thinking, well, let's try to look for liquid, and when we say water, I mean H2O. Dihydrogen oxide, I guess. So this one right here, H2O. And so what we're going to do then is try to find out then around a star, what distance around that star is suitable to have liquid water on that planet. And so what we do is we call something the habitable zone. So this is a place, or this, let's say this is a region where you could find liquid water. This is the main idea behind it. Now, this is very, very complicated to actually calculate, but let's just start looking at some of the basics of it. So if we want to find out where there's liquid water, well, water can be a liquid, at least on Earth, between 0 degrees Celsius and 100 degrees Celsius. Or we could do it in Kelvin if we want. That would be 373 Kelvin until 273 to 373 Kelvin. That's sort of where we're looking. Now, we're making a lot of assumptions here, and they may be dodgy. So, for example, we can only have liquid water on Earth like this, and that's because we have an atmosphere. And because we have an atmosphere, that allows water to be liquid at this temperature. So we're being a bit dodgy here, because we're going to then assume that the planet, this exoplanet we're looking at, we're going to just look for places where the temperature is between 0 and 100. In other words, we're going to completely forget about the fact that it might have an atmosphere and things like this. So this zone here is actually nicknamed the sort of Goldilocks zone. I don't know if you ever heard of that story. It's a child's story. Whoops, I better write it a little bit clearer. I know as a child, at least, we learned about this story. At least in Canada we did. So I'm not sure. I think it's spelled like this, Goldilocks. So it was a story about, was it a girl who goes into a house? I can't remember the exact details, but I do know that, there was something about, things being too hot or too cold or just the right temperature. And that's the idea behind this, that let's say we have the star here in the center, and around that star we have a region. So what we can do is we can calculate that region, the region where around that star here, anything within it here, we're going to say it's too hot. And that's because you're too close to the star. And then anything, as you go farther away, it gets cooler around it. Oops, I'm just trying to draw a nice ring around this. I'm not really the best artist here. And anything, let's say, outside of that, we could say it's too cold. In other words, water would be in a solid form. Here it would be in a gas form. So see here, if you had any water, it would basically be in a gas form. So it would evaporate out. Over here, the water, the H2O, would be in solid form. So in this case, it would be ice. So too cold. But in this region right here, we'd say, ooh, it's just right. See, that's what we call the habitable zone. It would be sort of this region between where it's too hot and too cold. That's what we call this habitable zone. Now to actually calculate it, that's tough. But we're going to attempt. So calculating the habitable zone. Now we're going to use something that's very, very crude. I almost cringe by doing this here. Okay, so this is a very, very crude method. So it's not exact at all. What we're going to do is we're going to use the Stefan-Boltzmann's law. So we're going to use this equation that the luminosity of a star is equal to 4 times pi times the radius of the star squared times sigma times t to the fourth. I've done some other videos about this. This right here is the sort of surface area of the star. This is Stefan-Boltzmann's constant, and this is the effective temperature. And actually, maybe we'll just define everything here. So we'll just write them all down. So L, that's the luminosity of a star, and remember that's the power. And what we can say then is that's the energy per given time. So that's in joules per second or watts. We have R. Now normally this right here would be the distance. This equation here works for a black body, and we're going to assume that the star is. And what it normally does, it tells you about the, given a surface temperature of the star and given its luminosity, you can find out how big the star is. The reason why this is really crude is because we're going to not take into account the fact that the planet has any sort of atmosphere or any other things like that. We're just going to say, assume the planet is a certain distance out from the star. And furthermore, we're going to assume, this equation here normally just works for stars. So what we're going to do is, it's like we're going to assume how big of a star would you have to have in order to have this temperature, this surface temperature on it. So normally this is the radius of the star, but here we're going to call this the distance from the star. Of course, that'll be in meters. So this is the really dodgy part. Now sigma, that's just the Stefan-Boltzmann constant. And we know that value is 5.67 times 10 to the negative 8. And T, that's the surface temperature normally of a star, or the effective temperature, because that's what a black body of that temperature would have. But in this case right here, we're going to call this then the surface temperature. Or let's just say the temperature of the planet. Yeah, we'll say it just like that. We'll be really crude here. So temperature on the planet. Now this will be in Kelvin. And so what we're going to do then is we're going to then use this sort of dodgy equation here. And here's the idea. The habitable zone then, so I'm going to just call it HZ for short. Okay, that's the habitable zone. That's going to be called HZ. See, HZ. The habitable zone is basically, look for, we're going to find the R value when the temperature is, let's say 0 degrees Celsius, which equals 273 Kelvin, and look for R when the temperature is equal to 100 degrees Celsius, which is 373 Kelvin. So what you'll do is you use this equation here, given the luminosity of the star, and what you do is you solve for R when T is either 273 or when T is 373. That's the idea behind it, given a luminosity. So let's actually do it. Let's calculate the habitable zone around our own sun. So we're going to see this is a very crude method of doing it, but I've given you the luminosity of the sun. Remember this little circle with a dot means solar here. So the luminosity of the sun is 3.8 times 10 to the 26 watts. In other words, it sort of emits this many joules per second. We're going to try to find the habitable zone, and we'll first calculate it in meters, and then we'll convert that to astronomical units. Remember, the astronomical unit is just the distance from the Earth to the sun, assuming a circular orbit, which is what we are assuming here. So then let's do it. Let's use this equation. We have L equals 4 pi r squared sigma t to the fourth. Well, we want to solve for r. Remember, the idea is to find r when t is one thing and when t is another thing. So we need to get r by itself. And we can do that. We can actually then say, well, r is going to be, well, r squared, I suppose, it'll be L, and I want to get rid of the 4 pi, so I'll divide both sides by 4 pi. And I also want to get rid of the sigma, it goes down here, and the t to the 4th. In other words, the only thing that stays on the top is the luminosity. I'm just going to pretty it up a little bit. So therefore, we have r then is equal to the square root. So technically it's plus or minus, but we're just going to keep the positive part. So 4 pi sigma t to the 4th. That's what we get for the distance that we're looking for. So then let's do it. Let's do it for the 2 different important distances, because this is sort of the idea behind it. So let's actually do it. Let's actually calculate it here. So at a distance, let's say here, maybe we'll call this the maximum distance. Because remember from this diagram back here, the maximum distance over here, that's when the temperature is going to be just about too cold. So we're going to make the temperature 0 degrees Kelvin. 0 degrees Celsius. So that's when T equals 0 degrees Celsius, which equals 273 Kelvin. And we're being crude here. We don't need to do the 0.15. I mean, we could be really sort of estimating here. So the maximum distance is when this happens. And we know the luminosity. So we have then that R equals, well, the luminosity, which is 3.8 times 10 to the 26. All that divided by 4 times pi times sigma, which is 5.67 times 10 to the negative 8. That's just a constant, times the temperature, which in this case is 273 to the power of 4. And I'm going to take the square root of that. And I'll get my answer. So I'll use my good old pal calculator. Whoops, where'd it go? There it is. And I'm going to just try to calculate this. So I'm actually going to do the bottom part first, because it seems a bit more complicated. So I'm going to just do the bottom. So, whoops, I need to do 273 and take that and make it to the power of 4. I'm going to take that answer and multiply that by Stefan Boltzmann's constant, 5.67 times 10 to the negative 8. I'm going to take that and multiply that by 4 times pi. That's the bottom. And I'm going to take all that, I'm going to take the top divided by that answer. So I'm going to say 3.8 times 10 to the power of 26. That's what this right here was. 3.8 times 10 to the 26. And I'm going to divide that by the answer, because that was what I last had here. Right? That was the bottom, so to speak. That was the denominator. And then I take the square root of that answer. And I end up with a value of 3. Yeah, let's say something like that. So 3 times 10 to the power of 11. Something like that. So away I go. So 3.1 times 10 to the 11, roughly. So R equals about 3.1 times 10 to the 11 meters. There we go. And so I can maybe then convert that to astronomical units. Remember, whoops, I'm trying to pretty it up, but I'm actually making it look worse. I'll just rewrite it again. So 3.1 times 10 to the 11 meters. But don't forget that 1 AU is 1.5 times 10 to the 11 meters. And so I want to find out how many of these fit into this. So I'm going to take this answer here and divide that by 1.5 times 10 to the 11. Oops. I better be careful here. So the answer divided by 1.5 times 10 to the power of 11. There we go. And then I get an answer of around 2. So let's say 2.1 astronomical units. So I'll say, therefore, that's this radius right here. That's 2.1 AU. That's the sort of maximum distance